My name is Alexander Eberlein and I'm a co-worker of Professor Reschke from the University of Paderborn at the Institute of Applied Mechanics. And I have to say my presentation is not dealing with thermomechanical fatigue, but everybody is invited to stay here and listen to the presentation. Good afternoon, dear ladies and gentlemen. It's a pleasure for me to present here our investigations on the effect of varying loading directions and loading levels on the crack growth at 2D and 3D mixed mode loadings. So I would like to start my presentation with challenges in fracture mechanical estimation, and after that I want you to explain the performed test series on the fatigue crack growth at under variable cyclic loading amplitude, for which this CDSR specimen and the loading device was used to. And the main point in my presentation will be the experimental results on crack growth due to changing loadings, and especially changing loading directions and loading levels. And at the end of my presentation I will give a summary of the results. So the fracture mechanical estimation of components containing cracks generally requires information about the component load, of course, and the geometry of the crack and the component, the material properties, and the fracture mechanical characteristics. So the component load here was the aspect which I studied here within this research, because usually the component load changes during the service life of a structure. So consequently, the real component load is a result of different changing loadings, which can lead to retardation or acceleration effects in fatigue crack growth. So my investigations are especially focused on the effect of varying loading directions, for example from a mode 1 loading to a mode 3 loading, and varying loading levels by interspersing block loads on the crack growth. So now I would like to explain you the performed test series. In the first test series, the loading direction was changed after a crack growth of 3.5 millimeters under mode 1 loading condition into in-plane mixed mode as well as spatial mixed mode situations. The R ratio here was constant at 0.1. So starting from a pure mode 1 loading at the crack, and changing of the loading direction into an in-plane mixed mode situation leads to a decreasing delta K1 and an immediately increasing delta K2. Moreover, such a changing loading direction has an influence on the crack growth rate too, as Sander and Richard already showed. In the second test series, different mixed mode block loads were interspersed in a mode 1 base load, in a mode 2 base load, and in a mode 3 base load to investigate the impacts on fatigue crack growth. The R ratio here was also kept constant at 0.1. Furthermore, the block loading ratio RB block and the maximum comparative stress intensity factor K block during the block load are defined by these both equations here. On the right figure, a typical AN curve of such a block loading test is shown with some characteristic variables which describe the retardation effect of such a low-high-low sequence. To perform these experiments, the so-called CDSR specimen and the loading device was used, and CDSR stands here for compact tension shear rotation. The specimen geometry with the characteristic dimensions is shown here on this. On the left side of the slide. The testing material was an heat-treated aluminium alloy 7075. The appropriate loading device consists of two sickles and so-called turrets where the specimen is fixed in. This concept enables crack growth investigating under pure mode 1 loading, pure mode 2 loading, pure mode 3 loading, as well as almost every combination of these 3 loading modes. only by changing the loading angles alpha and beta, and using only a uniaxial testing machine. So now I would like to show you the results of the first test series. Changing the loading direction from a mode 1 loading into in-plane mixed mode situations. So if the loading direction is not changed, then the crack grows like the blue curve here shows. By changing the loading direction from a mode 1 loading into pure mode 2 loading, the crack retards significantly, as you can see on this violet curve here. Other in-plane mixed mode situations lie in between these both curves. The crack growth retardation here is caused by the new crack growth direction, whereby the crack here kinks out of its previous orientation and has to initiate again in this new direction. The measured crack kinking angles coincides very good with the hypothesis by Richard. The results of changing loading directions from mode 1 loading into mixed mode 1+3 loading combinations shows quite similar retardation effects on the crack growth. Significant retardation effects were here obtained for K3 to K1 ratios between 1 and infinite. The crack growth retardation effects here are also caused by the new crack growth direction, whereby the crack here twists out of its orientation, of its previous orientation, and in the same time separates into multiple daughter cracks, so-called facets, which also has an influence on the crack growth rate. The measured crack twisting angles here coincides also very good with the hypothesis by Richard. Well, let's have a detailed look on this fractured surface here. This row of fractured surfaces show the facet formation depending on the mode 3 part on the total stress intensity factor K1 plus K3. It is obvious that facet develops at a specific mode 3 part on the total stress intensity factor of 0.37. Within these experiments, no facet developed below this ratio. At low K3 parts, as you can see here, the crack changes its growth direction continuously and smoothly without any facet initiation. Furthermore, the crack front is still coherent. So for characterizing the crack growth initiation behavior under mixed mode 1+3 loading combination, it is now necessary to quantify the facets. But this will be the next step of our investigations. So far, the results of the first test series. Now I would like to come to the results of the second test series, the effect of varying loading levels. This graph here shows an interspersed mode 1 block load in a mode 1 base load. And as you can see, the crack rests after mode 1 block load. Furthermore, an interspersed mode 3 block load in a mode 1 base load does not affect the crack growth. Other mixed mode 1+3 block loads lie between these both curves. Similar influences have interspersed in-plane mixed mode block loads in a mode 2 base load. Here, only a pure mode 2 block load leads to significant crack growth retardation in mode 2 base load. In comparison to that, interspersed mixed mode 1+3 blocks in a mode 3 base load always affect a crack in the mode 3 base load. This is also shown by the determined delay cycles NDI, which you can see here on this graph. In the right-hand side of the slide here, some typical fractured surfaces are shown which exhibit expected characteristics. For example, you can see a typical step here on the fractured surface under mode 2 base load, which occurred due to a pure mode 1 block load. The fractured surface resulting from interspersed mode 1, mode 3 block loads in a mode 3 base load reveal several facets and are relatively jagged. So let me summarize the results of these experiments now. The varying loading directions showed that a crack initiation in a new direction, as well as the facet formation, especially at mixed mode 1+3 loading combinations, are responsible for the crack growth retardations. Furthermore, the hypothesis by Richard shows quite good congruence between or with the measured crack kinking and the crack twisting angles. Significant advantages in durability are obtained by changing the loading directions in the regions of K2, 2K1 and K3, 2K1 between 1 and infinite. The varying loading levels show that the mode 3 block load does not affect the crack in the mode 1 base load. Not that shows loading parameters here. Furthermore, only a mode 2 block load leads to a crack growth retardation in the mode 2 base load. The influence of a mode 1 block load on crack growth in a mode 3 base load ever exists. The greatest advantages here in durability were achieved by identical loading modes of the block load and the base load. Thank you very much for your attention.